In almost every deep image James Webb takes of the infant universe, the same thing appears. Tiny, red, round. A faint crimson point, then another and another, until astronomers counted thousands of them across the dawn of time. No one is certain what they are. They might be the first giant black holes. They might be galaxies full of newborn stars. They might be something we have no name for yet. Tonight we sit with that mystery and follow where the newest evidence points. Settle in. If you enjoy quiet journeys to the edge of knowledge, a like and a subscribe help. And before we begin, where are you watching from and what time is it there? Start with a single point of light. Imagine one of the deep images the James Webb Space Telescope has sent back, the kind that takes your breath away when you first see it. A black field strewn with galaxies, thousands of them, spirals and smudges and golden ovals, each one a city of 100 billion suns. You could lose yourself in such an image for hours. And somewhere in that field, easy to overlook among all the grandeur, there is a tiny dot. It is small. It is round. It is red, a deep and saturated red, like a single drop of dried blood on a dark cloth. It does not look like much. You would scroll right past it. But that little red dot and the thousands like it may be one of the strangest things astronomy has found in a generation, because no one is sure what it is. Let that sit for a moment. We are talking about an object that the most powerful telescope ever built has photographed clearly, in large numbers, again and again, and we still cannot say with confidence what we are looking at. Not a blurry hint at the edge of detection, not a single ambiguous smudge that might be an artifact. Thousands of them, sharp and red and unmistakable, scattered all across the early universe, and the people who study them for a living are still arguing, in good faith, about whether they are galaxies or black holes or something that does not yet have a name. That is a rare situation in modern science. We are not used to looking straight at something and not knowing what it is. So tonight, I want to take our time with this. I want to walk slowly through what these objects are, how we found them, why they are so confusing, and where the newest evidence is finally beginning to point. There is no need to rush. This is a mystery still being solved, in real time, by real people, and we get to sit in the strange and lovely uncertainty of it together. Let us begin with the instrument, because the instrument is the reason this mystery exists at all. The James Webb Space Telescope is not like the telescopes that came before it. We had a great eye in the sky already, one that gave us decades of beautiful images, and it taught us an enormous amount. But it mostly saw the universe in the kind of light our own eyes see, ordinary visible light. Webb was built to do something different. Webb sees in infrared light that is redder than red, light with wavelengths too long for the human eye to perceive, the light of warmth and of great distance. And it sees that infrared light with a mirror far larger than anything we had flown before, a great golden mirror unfolded in the cold dark far beyond the moon, gathering the faintest whispers of light from the most distant reaches of space. Why does seeing in infrared matter so much? That is the first thread we will pull, and we will pull it properly in a little while. For now, hold on to this. The universe is expanding, and that expansion stretches light. The further away something is, the longer its light has traveled, and the more that light has been stretched on its journey toward us, shifted toward the red, and then beyond the red into the infrared. So the oldest, most distant light in the universe arrives at our telescopes not as visible light at all, but as infrared. To see the dawn of the cosmos, you must see in infrared. Webb was built precisely to look back to that dawn, and when it opened its eye and looked, it found, among the expected galaxies, something nobody had predicted. It found the dots. Here is how it happened. When Webb began its work, astronomers pointed it at carefully chosen patches of sky and ran great surveys, deep systematic stares meant to catalogue what lay in the early universe. Some of these surveys had names that sound like quiet poetry once you know them, names like Eiger and Fresco, projects designed to map the faint, distant galaxies of the cosmic dawn. And as the data came in and researchers began to sift through it, certain teams, including astronomers like Jorit Mathi and Ivo Labe and their colleagues, kept noticing the same odd thing. Over and over, in patch after patch of sky, there were these compact red sources, small, intensely red, far more of them than anyone expected. And around the years 2023 and 2024, as the pattern became undeniable, they gave the objects a name as plain and as honest as the objects themselves. Little red dots. I love that name, and I want to pause on it because there is something disarming about it. We are talking about objects at the very edge of the observable universe. Objects that may rewrite our understanding of how the first black holes and galaxies formed, and we call them little red dots. It is the name you would give them if you were simply describing what you saw on the screen, with no theory attached, no grand claim, just the visual fact. Little red dots. The name is a kind of scientific honesty. It says, we see these things clearly, and we are not yet going to pretend we know what they are. We are just going to call them what they look like. And what they look like, once you start counting, is everywhere. This is the part that turns a curiosity into a mystery. If Webb had found one strange red dot, or a handful, you might shrug. The universe is large and full of oddities. But that is not what happened. As the surveys deepened and more of the sky was examined, the dots kept appearing in field after field until the count climbed into the hundreds and then the thousands. They are not rare. By some estimates, around 1% of galaxies in that early epoch appear to host one of these objects. 1 in 100. That may not sound like a lot, but for a strange, unexplained, brand new class of object to make up 1 in every 100 sources at the dawn of time is staggering. It means these things were a common feature of the early universe, not a fluke. Whatever they are, the young cosmos made a great many of them. Sit with that contradiction for a moment, because it is the heart of why this matters. On one hand, these objects are abundant, common, ordinary in the statistical sense, a recurring feature of the early universe that shows up reliably wherever we look closely enough. On the other hand, we do not know what they are. Those two facts should not sit comfortably together. Usually, if something is common, we understand it, because we have many examples to study. But here we have thousands of examples and still no agreement. The dots are at once familiar, in that we see them constantly, and utterly mysterious, in that we cannot explain them. It is as though you kept finding the same unfamiliar object in every house you entered, in every drawer you opened, and no one, Not even the experts could tell you what it was for and remember where they are. These are not nearby objects sitting in our cosmic backyard where we might easily go and study them in detail. They are at the edge of the observable universe, their light stretched into the infrared by the long journey and the expansion of space, light that left them when the cosmos was only a small fraction of its present age. We are seeing them not as they are now, but as they were in the deep past, because their light has taken almost the whole age of the universe to reach us. When you look at a little red dot, you are looking at something that existed more than 13 billion years ago. You are looking, quite literally, into the dawn of time. We will unfold exactly what that means soon. So this is where we begin our journey. A telescope built to see the oldest light there is, a survey of the early universe, and, scattered through that survey in their thousands, a population of small, intensely red, point-like objects that no one anticipated and no one can yet fully explain. They are common and they are baffling. They are sharp and clear and right in front of us, and they refuse to tell us what they are. The obvious first question is the one a child would ask. If we can see them so clearly, why can we not just tell what they are? Why is a bright, well-photographed object such a deep mystery? The answer is that seeing something and understanding it are very different things, and the dots, as we are about to discover, are giving us a set of clues that seem to contradict one another, a forensic puzzle where every piece of evidence points in a different direction. Before we can read those clues, though, we need to understand the strangest thing about where these dots live, which is not really a place at all. It is a time. The deep past, the first chapter of the universe. And to understand how we can possibly be looking into the past, we need to talk about what it really means to look up at the sky. So settle in and let your mind grow quiet and wide, and let us follow the light of these little red dots backward across more than 13 billion years to the strange truth that every telescope is also a kind of time machine. Before we follow the light backward, let us stay a little longer with the dots themselves and with the quiet shock of their discovery, because the human side of this story matters too. Try to picture what it was actually like in those first months after Webb began returning data. For decades, astronomers had dreamed of this telescope. They had waited through delays and setbacks, through years of building and testing, for an instrument that could finally see the infant universe clearly. And when the images came, they were everything that had been hoped for, and then some. There were galaxies further away than anything seen before, structures from impossibly early times, a flood of discovery so rich that researchers could barely keep up. In the middle of that flood, the red dots were almost a distraction at first, a small recurring oddity in images full of grander things. It took a while for the oddity to become a mystery, and the mystery to become one of the central puzzles of the field. That is often how real discovery works. It is rarely a single bright moment of revelation. It is more often a slow accumulation of the same strange detail, noticed again and again, until someone steps back and says, "Wait, why does this keep happening?" The little red dots were like that. One compact red source is nothing. 10 is a coincidence. But when you have sifted through field after field and the same kind of object keeps appearing, small and red and far too common, the coincidence curdles into a question. And the question, once asked clearly, would not go away. Let me try to describe more precisely what these objects look like to the people studying them, because the visual character of the dots is part of the puzzle. In the raw images, they are unresolved. That is an important word, and I will translate it. When a telescope looks at a nearby galaxy, it can see its shape, its spiral arms, its sprawl, the way it spreads across a patch of sky. The galaxy is resolved, meaning the telescope can make out its structure. But the little red dots are not like that. They are points. They have no visible structure, no arms, no discernible width beyond what the telescope itself imposes on any point of light. They look, in other words, less like sprawling galaxies and more like single concentrated sources, as though all their light were pouring out of one extremely small region. For something at such a great distance to appear so compact, the light has to be coming from a region that is, by cosmic standards, astonishingly tiny. Hold that detail. It will matter enormously later. And then there is the color, the redness that gives them their name. This is not a subtle tint. These objects are dramatically red, redder than ordinary galaxies, red in a way that demands an explanation. In astronomy, redness can mean several different things, and untangling them is part of the whole challenge. Something can look red because it is genuinely far away and its light has been stretched by the expansion of the universe. Something can look red because it is shrouded in dust, which scatters away the bluer light and lets the redder light through, the same way the sun turns red and gentle when it sinks through the thick air at sunset. And something can look red because of the particular kind of object it is and the particular light it emits. The dots are red for reasons that, as we will see, combine more than one of these, and in a pattern that is genuinely strange. Their light, examined carefully, does something that should not be easy to arrange, and that strangeness is one of the central clues. We will look closely at it soon. There is one more thing to establish before we travel back in time, and it is perhaps the most unsettling thing of all. The little red dots are not spread evenly through cosmic history. They are concentrated in a particular era, the early universe, the first billion years or so after everything began. They appear in great numbers in that early epoch, and then, as we look at later and later times, closer and closer to our own, they thin out and seem to largely disappear. They are a feature of the cosmic dawn specifically. Whatever they were, they flourished in the universe's infancy and then faded, leaving few or no clear counterparts in the universe we see around us today. That alone is a profound clue and a profound puzzle. It tells us we are looking at something that belonged to a specific, vanished chapter of cosmic time, a kind of object the young universe made in abundance and the older universe does not. What changed? What were the conditions of that early era that produced so many of these things, and why did those conditions pass? I want you to feel the weight of that calmly, the way you might feel the weight of a very old photograph. These objects are not just far away in space. They are far away in time, and they belong to a world that no longer exists, the universe as it was in its first chapter, hot and dense and young and rapidly building its first great structures. We cannot visit that world. We can only receive the light it sent, light that has been traveling toward us for almost the entire history of the cosmos, and try to read, in that ancient light, the story of what these objects were, And the early hints of that story are already enough to make cosmologists uneasy, because whatever the dots turn out to be, the simplest readings of the evidence keep suggesting something that should not be possible so soon. If they are galaxies, they seem to be too massive and too compact for such an early time. If they harbor black holes, those black holes seem to be too large to have grown so quickly after the beginning. Either way, the dots seem to be telling us that the early universe built big things faster than our theories say it should have been able to. That is why, in the first wave of excitement, some astronomers spoke, half seriously, of objects that might break the models. Things that did not fit the careful picture we had assembled of how the cosmos grows. The little red dots became part of a larger unease, a sense that the early universe Webb was revealing was richer and more precocious and stranger than we had been prepared for. That unease is the real engine of this story. It is not just that we have found a new kind of object. It is that the new object seems to challenge our understanding of how the universe assembled itself in its earliest days. And that is why thousands of small red points, easy to scroll past in a glorious image, have become one of the most discussed mysteries in modern astronomy. They are a loose thread, and when you pull a loose thread in cosmology, you sometimes find that a great deal more is connected to it than you expected. So let us pull it. Let us follow these dots back to where and when they truly are. To do that, we have to understand the deepest and most beautiful fact about looking at the sky. The fact that to look out into space is always, unavoidably, to look back into time. Let your thoughts settle and widen, and come with me to the edge of the observable universe, and to the first billion years. There is a quiet thrill in standing at exactly this kind of threshold, the moment before an explanation arrives, when the evidence is in hand but the meaning is not yet fixed. We are living through that moment with the little red dots right now, so let us not hurry it. Let us understand, first, what it means that their light is so old, and why looking at them is the closest thing we have to remembering the universe being born. Here is something so familiar that we forget how strange it is. When you look up at the night sky, you are not seeing the universe as it is. You are seeing it as it was. Light is fast, the fastest thing there is. But it is not infinitely fast. It takes time to travel, and space is so vast that the time light takes to cross it becomes enormous. The light from the sun takes about 8 minutes to reach us, which means you never see the sun as it is right now. You see it as it was 8 minutes ago. If the sun were to vanish this instant, you would not know for another 8 minutes, because the last of its light would still be on its way. Look at the moon, and you see it as it was just over a second ago. Look at the next nearest star, and you see light that left it years ago. The further out you look, the further back in time you see. This is the single most important idea for understanding the little red dots, so let us make it solid before we go on. Every time you look at something distant, you are looking into the past, because the light you are receiving left that object long ago and has only now completed its journey to your eye. A telescope, then, is not only a device for seeing far away, it is a device for seeing long ago. The deeper into space it can peer, the deeper into the past it can see. To look across the universe is to look down through its history, like reading the layers in ancient rock, each deeper layer older than the one above. Now, Stretch that idea to its limit. The light from the little red dots has been traveling toward us for more than 13 billion years. More than 13 billion. The universe itself is only about 13.8 billion years old. So the light from these dots left them when the universe was very young, a small fraction of its current age, in the first chapter of cosmic history. We are not seeing what the dots look like now. We have no idea what they look like now, or even whether they still exist in any form. We are seeing the light they cast in their own distant youth, in the youth of the whole cosmos. Light that set out across the dark when the universe was new and has only now, after traveling almost the entire age of everything, arrived at the golden mirror of our telescope. Let that land properly. When that light began its journey, there was no Earth, there was no Sunday. The atoms that would one day become your body were scattered who knows where, not yet gathered into a star, let alone a planet, let alone a person. The light from these dots is older than the ground you are lying on, older than the world, older than the star that warms it. It has been crossing the emptiness for billions of years, indifferent and patient. And we built a telescope and caught it. And in catching it, we caught a glimpse of the universe as an infant. There is something almost unbearably moving in that, if you let yourself feel it. We are looking at baby pictures of the cosmos, developed from light that has been in transit since before our world was a possibility. But how do we know the light is that old? How do we measure the distance and the age of something so impossibly far away? This is where we have to talk about redshift, the tool that lets astronomers read the depth of time in a beam of light. I will build it gently, because it is the key that unlocks everything. Light is a wave, and waves have a length, the distance from one crest to the next. For light, that wavelength is what we perceive as color. Short wavelengths look blue, longer wavelengths look red. Stretch a wave of light, make its wavelength longer, and its color shifts toward the red end. This is the essential idea. Now here is the crucial fact about our universe. It is expanding. Space itself is stretching, growing, carrying distant galaxies ever further apart. And as a beam of light travels across that expanding space, the space it is moving through stretches, and the light stretches with it. Its wavelength grows longer during the journey. Its color shifts toward the red. We call this redshift, and the amount of redshift tells us how much the universe expanded while the light was in transit, which tells us how long the light has been traveling, which tells us how far away and how far back in time the source is. The more distant the object, the longer its light has traveled, the more the universe has expanded during that journey, and so the more its light has been stretched, the greater its redshift. Astronomers measure this with a number, and they call it Z. A small z means a small stretch, a relatively nearby and recent object. A large Z means the light has been enormously stretched, that it comes from far away and long ago, and the little red dots have large redshifts. Most of them sit beyond a redshift of 5, and many further still, which places them squarely in the first billion years of cosmic history, deep in the era astronomers call the cosmic dawn. So now you can see why Webb had to be an infrared telescope, and the thread from earlier ties off. Light that began as ordinary visible light, or even as ultraviolet, leaving these objects in the young universe, has been stretched so much on its long journey that by the time it reaches us, it has been shifted all the way into the infrared. To the human eye and to the old visible light telescopes, that ancient light is invisible, stretched beyond what we can see. Only an instrument built to catch infrared, like Webb, can gather it. The dots are red in our images partly because of dust and their own nature, as we will explore, but they are red also in this deeper sense, that the very fabric of the expanding universe has reddened their ancient light across billions of years of travel. They are red because they are old. Let us put numbers on this cosmic dawn, gently, because the numbers are part of the wonder. The universe is about 13.8 billion years old. The little red dots appear in great abundance around 600 million years after the Big Bang. 600 million years sounds like a long time, and by human measure it is unimaginable. But against the full age of the cosmos, it is the very beginning. If you imagine the whole history of the universe compressed into a single year, with the Big Bang on the 1st of January and this present moment at the last midnight of the 31st of December, then 600 million years after the beginning falls in the middle of January, the little red dots flourished in the first weeks of the cosmic year. They are a feature of the universe's infancy, the time when the first stars and galaxies were only just beginning to light up the darkness. And here is the detail that makes them stranger still. They do not last. As we look at later and later cosmic times, which is to say at smaller redshifts, closer to our own era, the dots thin out and largely vanish. They are abundant in that early window, and then they fade from the record. By the time the universe is a couple of billion years old, the little red dots, as a clear population, are mostly gone. Whatever they were a phenomenon of the cosmic dawn specifically, something the young universe produced in great numbers under conditions that later passed away. They flared into being in the first chapter, and then, as a recognizable class, they faded. Think about what that implies. We are not looking at some permanent fixture of the cosmos that simply happens to be far away. We are looking at a transient feature of a vanished era, a kind of object that belonged to the universe's youth and does not clearly belong to its maturity. That is a clue of the deepest kind. It tells us that the dots are tied to the special conditions of the early universe, to the way matter was arranged and behaving in those first hundreds of millions of years, conditions that no longer hold today. To understand the dots is therefore to understand something about that lost early world, the furnace of creation in which the first great structures were forged. So hold this picture as we go forward. The little red dots are not just distant points of light. They are messages from the universe's infancy, written in light that has been stretched and reddened across more than 13 billion years of expanding space, carrying news of a chapter of cosmic history that ended long before our world began. They cluster in the first billion years and then fade away, and in their ancient, stretched, crimson light, there are clues, contradictory and confusing clues about what they were. We have learned to look back in time. We have learned to read the depth of that time in the redshift of the light. Now we have to become detectives and read the clues themselves, because the clues, as we are about to see, do not agree with one another. Let us linger in that early universe a little longer, because to understand the dots, we have to feel what kind of world they lived in, and it was a world utterly unlike our own. Go back in your mind to the time before there were any stars at all. After the Big Bang, the universe was hot and dense and almost perfectly smooth. a near uniform fog of hydrogen and helium gas, glowing and then cooling, with no points of light anywhere. For a long stretch, hundreds of millions of years, there was simply darkness, a cosmos full of gas and unlit, a great patient waiting. Astronomers sometimes call this the cosmic dark ages, and the name is apt. There were no suns, there was no starlight. There was only the slow gathering of gas under gravity, clumps drawing together, growing denser, until at last, somewhere, the first clump grew dense and hot enough at its core to ignite, and the first star was born, and light returned to the universe for the first time since the afterglow of the beginning faded. The little red dots belong to the era right after that first light, the cosmic dawn, when the darkness was ending and the universe was lighting up. This was a time of furious creation, of the first stars and the first galaxies assembling out of the primordial gas, of structure emerging from smoothness. It was a brief, intense, formative chapter, the universe building its first great things. And it is exactly here, in this chapter of first light and first structure, that the dots appear in abundance. Whatever they are bound up with the universe's first creative outburst, the moment it stopped being a smooth, dark fog and started becoming the structured cosmos of galaxies we know. I find it helps to return to the calendar image and make it more vivid, because the timescales here are so far beyond intuition that we need a handle. Compress all of cosmic history into 1 year. The Big Bang is the first instant of the 1st of January. The cosmic dark ages fill the opening days. The first stars flicker on in early January. The little red dots blaze in the 2nd and 3rd weeks of January. And then consider where we are. Our Sun and Earth do not even form until the start of September, 2/3 of the way through the cosmic year. The dinosaurs come and go in late December. All of recorded human history, every empire, every life that has ever been written down, occupies the final few seconds before midnight on the 31st of December. The little red dots, then, are January objects, and we are looking at them from the last second of the year across nearly the entire span of cosmic time. The distance in time between them and us is almost the whole history of everything. Now, you might reasonably wonder how confident we really are about all this. It is one thing to say an object looks red and therefore might be distant. Could the dots not just be nearby reddish objects pretending to be far away? This is exactly the kind of doubt good scientists raise, and it has been tested. For many of the dots, astronomers have not just measured their color but taken their spectra, spreading their light out into its component wavelengths, the way a prism spreads sunlight into a rainbow. In that spread out light, certain features appear, fingerprints of specific elements like hydrogen at specific wavelengths. By measuring how far those known fingerprints have been shifted toward the red, astronomers can pin down the redshift precisely, and through it the distance and the age. For a good number of the dots, these spectra confirm it. They really are at high redshift. They really do come from the first billion years. This is not a guess from color alone. It is a measurement, read from the stretched fingerprints of elements in their ancient light. The dots are genuinely creatures of the cosmic dawn, and that brings a particular kind of feeling, one the best science often carries, a mingling of awe and a gentle melancholy. Because these objects, whatever they were, are almost certainly gone now, or transformed beyond recognition. 13 billion years have passed in their own frame since the light we see departed. Whatever a little red dot was, it has had all of cosmic history to evolve, to grow, to die, to become something else entirely. The thing itself is long vanished. What remains is only the light, this faint red message still arriving, the last word of an object that ceased to be what it was an eternity ago. When we study the dots, we are, in a sense, studying ghosts, reading letters from senders who are long gone, piecing together the lives of objects that finished their stories before our planet was a glimmer. There is loneliness in that, and there is also a strange intimacy, a connection across the entire age of the universe, a message received at last after the longest possible silence. Sit with that for a moment before we go on, because it frames everything that follows. The clues we are about to examine, the strange colors and the broad emission lines and the missing signals, are all encoded in light that is this old, this far traveled, this much a relic of a vanished world. We are not examining objects we can poke and prod. We are examining their final light and trying to reconstruct, from that single faint beam, what kind of thing could have sent it. It is the ultimate cold case. The witnesses are gone. The scene is 13 billion years in the past. All we have is the light and what we can read in it. So let us turn now to reading it. Let us look closely at the actual clues the dots present, the specific, peculiar, contradictory features of their light that have astronomers so divided. Because the deepest strangeness of the little red dots is not simply that they are far away or old or abundant. It is that when you examine them carefully, they show a combination of features that no single familiar kind of object should be able to produce all at once. They are red and yet also blue. They are point-like and yet seem enormously powerful. They show the violent signatures of fast-moving gas and yet hide the signals that such violence usually brings. Each clue, on its own, points toward a different answer. Together, they point nowhere we have been before. Let us examine them, one by one, and feel the shape of the riddle take form. And take, before we do, one slow breath of perspective. We began this part with the simple fact that to look out is to look back. We end it holding the full weight of that fact, light older than the Earth, gathered from a vanished chapter of the cosmos, carrying clues we are only beginning to decode. It is a quietly staggering thing that a species on a small wet world, in the last second of the cosmic year, can catch the infant light of the universe and argue thoughtfully about what it means. Whatever the dots turn out to be, the fact that we can even ask the question is its own kind of marvel. So let us ask it carefully now, and look hard at the clues, and let the riddle show us its true shape. Let your mind stay in that early universe a moment longer, the dark just lifting, the first lights kindling in the gas, the cosmos building its first great things in a burst of creation we can still faintly watch. That is the stage on which the dots appeared. Now, let us study the actors themselves. What follows is a kind of forensic examination, clue by clue, of light that has waited 13 billion years to be read. Let us give it the patience it has earned. Now we become detectives. We have a body of evidence, the light of the little red dots, and we are going to lay out the clues one by one, the way an investigator lays out the facts of a case on a table. And what makes this case so gripping is that the clues do not fit together. Each one, examined alone, points toward a particular kind of answer. but the answers they point toward are different, and some of them seem to rule each other out. Let us look at them carefully and feel the contradiction build. The first clue is the one you already know, the color, but it is stranger than simply being red. When astronomers spread out the light of these dots and looked at how bright they are at different wavelengths, they found something peculiar. The dots are very red in the optical part of their light, the part that corresponds to ordinary visible colors in their own frame. That much fits the name. But in the ultraviolet, the bluer, more energetic part of their light, they are surprisingly bright, surprisingly blue. So a single dot is both unusually red in one part of its spectrum and unusually blue in another. If you draw a graph of the dot's brightness across wavelengths, the line dips in the middle and rises on both ends, making a shape that astronomers have come to call a V-shaped spectrum, blue on one side, red on the other, with a valley between. Sit with how odd that is. Most objects have a fairly simple color story. A cool star is red, a hot star is blue, a dusty galaxy is reddened across the board. But the little red dots are doing two things at once, showing both a strong red component and a distinct blue component, as though two different kinds of light from two different kinds of source were being added together in the same tiny object. That V shape is one of the defining signatures of the dots, and it is already a puzzle. What single object produces light that is both strongly red and strongly blue, with a dip in between? Hold that question. It will turn out to be one of the most important clues of all. The second clue is the compactness, which we touched on before and now need to weigh properly. The dots are point-like, unresolved. When the telescope looks at them, it cannot make out any extended shape, any spread, any structure. All their light appears to come from a region so small that, even with Webb's sharp eye, it registers as a single point. Now think about what that means for the red part of their light especially. If that red light is coming from stars, from a galaxy full of stars, then to be packed into so small a region, those stars would have to be crammed together at an extraordinary density, far denser than any normal galaxy, a city of suns squeezed into a space that ought to hold a small town. That is physically possible, but deeply uncomfortable. It would mean these are the most compact, densest concentrations of stars we have ever seen, which is its own kind of problem. The compactness pushes us, uneasily, toward the idea that the light is not coming from a sprawling population of stars at all, but from something far more concentrated, something like a single central engine, something like a black hole. And that brings us to the third clue, which is the most dramatic, and which seems at first to settle the question. When astronomers took spectra of the dots and looked closely at the light from hydrogen, they found that the hydrogen emission lines were broad. Let me unpack that, because it is the crucial piece. When hydrogen gas glows, it emits light at very specific, sharp wavelengths, a narrow spike in the spectrum. But if that gas is moving, swirling at high speed, some of it coming toward us and some moving away, then the light gets smeared out, shifted slightly bluer where the gas approaches and slightly redder where it recedes. The sharp spike becomes a broad hump. The width of that hump tells you how fast the gas is moving. And in the little red dots, the hydrogen lines are broad, which means the gas producing them is moving very fast indeed, at speeds of thousands of kilometers per second. What makes gas swirl that fast? On Earth, in galaxies, in ordinary settings, gas does not move at thousands of kilometers per second. To whip gas to such speeds, you need an enormous concentration of gravity in a very small space. You need something pulling that gas around at a furious pace. And the classic source of exactly this signature, broad, fast hydrogen lines from a tiny central region, is a feeding black hole. When a supermassive black hole pulls in surrounding gas, that gas spirals inward, forming a swirling disk, and as it whirls around the black hole at tremendous speed, it glows with broad emission lines just like these. So this third clue, the broad lines, points hard toward a black hole at the center of each dot, a massive black hole in the early universe, dragging gas around itself at thousands of kilometers per second. Combined with the compactness, the picture seems to snap into focus. These are not galaxies. These are early supermassive black holes, blazing as they feed. And if that were the end of the clues, the case would be closed. But it is not the end, because there are two more clues, and they are clues of absence, things that should be there if these are feeding black holes and are not. And it is these missing pieces that blow the case wide open again. Here is the fourth clue, the first great absence. When a supermassive black hole feeds, when it drags gas into a furiously hot swirling disk, that process does not only produce broad hydrogen lines, it produces X-rays, lots of X-rays. The gas spiraling into a black hole gets heated to such extreme temperatures that it blazes in high-energy X-ray light, and this X-ray glow is one of the most reliable signatures of an active feeding black hole. Across the universe, when we find these black hole engines, we find them shining in X-rays. So if the little red dots are feeding black holes, as the broad lines suggest, they should be pouring out X-rays. We have looked, and for the most part, the X-rays are not there. The dots are strangely, stubbornly quiet in X-rays, far quieter than feeding black holes are supposed to be. The signature that should confirm the black hole is missing, and here is the fifth clue, the second great absence, and it cuts the other way too. When a black hole feeds and shines, much of its fierce light tends to strike surrounding dust, heating that dust until it glows in its own infrared light, a warm glow at particular longer wavelengths. This hot dust signature is another standard fingerprint of a dust-shrouded feeding black hole. If the dots are reddened because they are wrapped in dust around a blazing black hole, we would expect to see that dust glowing hot. And again, when we look, the expected hot dust glow is largely missing or weaker than it should be. The dust signature that should accompany the reddening is not behaving as it should. Do you feel the trap the dots have set for us? Lay the clues side by side. The broad hydrogen lines say black hole. The compactness says black hole, or at least something extraordinarily concentrated. But the missing X-rays say not a normal feeding black hole. The missing hot dust says not a normal dust-shrouded one either. And the V-shaped spectrum, blue and red at once, fits no simple single picture cleanly. Every clue that points toward an answer is contradicted by another clue that points away from it. The evidence convicts and acquits the same suspect in the same breath. This is the true shape of the riddle. It is not that we have no idea what the dots could be. It is that we have several ideas, each supported by some of the evidence and refuted by the rest. The dots look like feeding black holes in some ways and refuse to behave like feeding black holes in others. They look like impossibly dense galaxies in some ways and like single points of engine light in others. They are a contradiction wearing the same small red face, and any explanation that hopes to succeed has to account for all of it at once: the redness and the blueness, the compactness, the fast gas, and the strange silences where signals ought to be. So now the real work begins. We have the clues. We have felt how they pull against one another. The question is whether any single kind of object, or any new kind of object, can hold all these contradictory clues together in one coherent picture. There are three main suspects that astronomers have brought to the table, three candidate answers to what the little red dots are. Let us bring them in, one at a time, and test each against the evidence, and see how each one explains some of the clues beautifully, and then stumbles on the rest. This is where the mystery deepens before it begins, at last, to resolve. Let us go back through the clues more slowly, because each one carries an intuition you can actually feel, and feeling them is what makes the contradiction real rather than abstract. Take the broad hydrogen lines again, and let me give you the everyday version of the physics. You already know this effect, even if you have never named it. Think of an ambulance racing past you with its siren on. As it approaches, the pitch of the siren sounds higher. As it passes and recedes, the pitch drops lower. The sound waves are squeezed higher in pitch when the source moves toward you and stretch lower when it moves away. Light does exactly the same thing. Light from something moving toward you is shifted bluer, and light from something moving away is shifted redder. Now imagine a cloud of glowing gas whirling in a circle at tremendous speed. One side of the circle is sweeping toward you, its light shifted blue. The other side is sweeping away, its light shifted red. All of it blends together in your telescope, and the sharp, single color of the hydrogen smears out into a broad band. Blue shifted on one edge, red shifted on the other. The width of that smear is a direct measure of how fast the gas is whirling. In the little red dots, the smear is wide, which means the whirling is fast, thousands of kilometers per second. That is not the gentle drift of gas in a calm galaxy. That is gas caught in the grip of something with a fierce and concentrated gravity, swung around at a speed that demands a massive compact engine at the center. That is the fingerprint of a black hole feeding, and it is written clearly in the light of the dots. Now hold that beside the silence in the X-rays, and feel the genuine wrongness of it. When gas falls toward a black hole, it does not fall quietly. It piles up into a searingly hot disk, friction heating it to temperatures that make it blaze in X-rays, the high-energy light of the most violent processes in nature. Every time we have found a feeding black hole of this kind across the cosmos, this X-ray glow has been there, a reliable beacon. It is so reliable that astronomers use X-rays as one of the primary ways to hunt for hidden black holes. So we pointed our X-ray eyes at the little red dots, expecting the beacon, and mostly there was nothing. A faint murmur at best, far less than the broad lines led us to expect, and in many cases, nothing detectable at all. It is as though you found a fire that smeared the gas around it with all the heat and motion of a roaring blaze, and yet gave off almost no light of its own. The motion says inferno, the X-rays say silence. Both cannot be simply true of an ordinary feeding black hole. And that is the knot at the center of the whole problem. The missing hot dust is the same kind of wrongness from a different angle. Suppose, to save the black hole idea, you say the X-rays are simply hidden, buried under a thick shroud of dust that absorbs them. That is a reasonable thought, and dust does redden and obscure things. The reddening of the dots could be dust, the same way the sun goes red and soft as it sinks through the thick, dusty air at the horizon. But here is the catch. When dust absorbs all that fierce energy from a feeding black hole, it heats up, and hot dust glows in its own particular infrared light. So if a thick dust shroud were hiding the X-rays and reddening the light, that shroud should itself be glowing warmly in the infrared, and we should see that glow. We mostly do not. The dust that would be needed to hide the black hole does not announce itself the way hot dust should. So the easy escape, just hide it behind dust, runs into its own missing signal. The shroud that would explain one absence creates another. And then there is the sheer abundance, which is a clue of a different kind, not about a single dot, but about the whole population. We said the dots are common, around 1 in 100 early galaxies. If each one harbors a feeding supermassive black hole, then the early universe was absolutely teeming with such black holes. Far more of them packed into that early epoch than our models of how black holes grow had ever predicted. When astronomers compare the number of dots to the number of known bright feeding black holes, the quasars that we had catalogued at similar early times, the dots outnumber the expectation by a large factor, so even the count is a problem. There should not be this many of whatever they are, this early, if they are the kind of object we already understood. The abundance itself breaks the budget. Step back now and look at the whole table of evidence, and notice what kind of situation we are in, because it is a particular and instructive one. This is not a case where we are missing data. We have spectra. We have colors across many wavelengths. We have X-ray observations and infrared observations and counts across the sky. We are drowning in data. The problem is not too little evidence. The problem is that the evidence we have, taken all together, does not fit any object we already know. Every familiar suspect explains part of the picture and fails on the rest. And that is actually one of the most exciting situations in all of science, even though it feels like confusion, because it usually means one of two things. Either we are misreading one of the clues, and a subtle effect is fooling us into seeing a contradiction that is not really there, or we are genuinely looking at something new, a kind of object or a kind of configuration that we did not have in our catalogue of the universe. Both possibilities are thrilling. One means we are about to learn something subtle about physics. The other means we are about to add a new entry to the list of things the universe contains. I want you to hold the discomfort of the contradiction without rushing to resolve it, because the discomfort is honest, and the scientists living through this are sitting in exactly the same discomfort. They do not have a tidy answer handed down from authority. They have this same confusing table of clues, and they are arguing carefully and respectfully and intensely about how to read it. That argument is not a sign that science is failing. It is science working out loud on a genuinely hard problem in real time. We are watching the process itself, the messy and beautiful middle of discovery before the textbooks are written. So let us now bring in the suspects, the candidate explanations that astronomers have proposed to hold all these clues together. There are three main ones: a galaxy bursting with hidden stars, an early black hole feeding in the dark, and the unsettling possibility of something with no name. Let us examine each and watch how each one shines on some of the clues and breaks on others, until we arrive at the newest idea, the one that may finally hold the whole strange picture together. Keep the table of clues in your mind as we go, the way a detective keeps the photographs pinned to the wall: the V-shaped light, the point-like compactness, the fast whirling gas, the silent X-rays, the missing hot dust, the sheer impossible abundance. Any true answer must explain every one of them, not just the convenient few. That is a demanding standard, and it is exactly the standard the real explanation will eventually have to meet. So, let us hold each suspect to it, honestly, and see what survives. So let us bring in the suspects. There are three main candidates for what a little red dot is, and we will question each in turn, holding it against the table of clues, watching it explain some and stumble on others. The first suspect is a galaxy bursting with stars hidden behind dust. In this picture, a little red dot is a real galaxy, an immense and frantic episode of star formation. Thousands upon thousands of new stars igniting in a small region all at once, blazing with light and wrapped in a thick veil of dust that the young stars have produced. The dust absorbs the bluer light and lets the redder light through, which is why the object looks so red. We see this kind of thing in the nearer universe, dusty starburst galaxies glowing red behind their own veils, furnaces of stellar birth. It is a known phenomenon, and it explains some of the clues well. It explains the redness through the dust. It can begin to explain the compactness if the burst of star formation is concentrated in a small dense core. For a while, this was a leading idea, and it remains a serious possibility for at least some of the dots. But test it against the harder clues, and it begins to strain. The broad hydrogen lines are the first problem. A galaxy full of stars, even a frantic one, does not naturally whirl its gas at thousands of kilometers per second in a tiny central region. Star formation stirs gas, yes, but not generally to those speeds in that pattern. The broad lines are much more naturally made by gas swirling around a massive compact object than by a crowd of stars. So the starburst idea has to work hard to explain the very feature that most cleanly suggests a black hole. And then there is the abundance and the density. To make the dots this compact and this common and this red purely with stars, you need to pack stars at extraordinary densities, and you need a great many such objects, more than our picture of early galaxies comfortably allows. The starburst suspect explains the gentle clues and struggles with the violent ones. It is not ruled out, especially for some fraction of the dots, but it does not sit easily with the whole picture. The second suspect is the one the broad lines keep pointing to, an early supermassive black hole feeding. In this picture, at the center of each dot is a black hole of enormous mass, already grown large in the young universe, pulling in surrounding gas. That gas swirls inward at tremendous speed, producing the broad hydrogen lines. The intense light of the feeding produces the brightness, and the whole thing is so concentrated that it appears as a point, which fits the compactness perfectly. This is the active galactic nucleus idea. The notion that the dots are a newly discovered population of feeding black holes in the cosmic dawn, and it explains the most dramatic clues beautifully. The broad lines, the compactness, the power, all flow naturally from a feeding black hole. But you already know where this suspect stumbles, because we laid the trap ourselves. The missing X-rays. A feeding black hole of this kind should blaze in X-rays, and the dots mostly do not. And the missing hot dust, which undermines the easy escape of saying the X-rays are simply hidden behind a shroud. So the black hole suspect, which explains the violent clues so well, runs straight into the two great absences. If these are feeding black holes, they are feeding black holes that have somehow gone quiet, in exactly the ways feeding black holes are not supposed to go quiet. The suspect with the strongest motive has an alibi we cannot explain, and so we arrive at the third suspect, which is not really a suspect at all, but a confession of ignorance, and it is the most unsettling of the three. Perhaps the little red dots are something genuinely new, not a known kind of galaxy, not a known kind of feeding black hole, but a kind of object or a kind of configuration that does not yet exist in our catalogue of the universe. Something the early cosmos produced that has no clear counterpart today and no entry in our textbooks. This possibility is not anyone's first choice, because science prefers to explain new things with known ingredients before inventing new ones. But the persistent failure of the familiar suspects to account for all the clues keeps this third possibility on the table. Maybe we are not misreading the evidence. Maybe the evidence is telling us, plainly, that the young universe contained things we have never seen in the mature universe, things that formed under conditions that no longer exist, and then faded as those conditions passed. Sit with that third possibility for a moment, because it carries a particular kind of vertigo. We like to believe that the universe is, by now, mostly catalogued, that the great categories of cosmic objects, the stars and the galaxies and the black holes, are known, and that what remains is to fill in details. The little red dots whisper that this confidence may be premature. They raise the possibility that the early universe was not merely a younger version of the one we know, populated by the same kinds of things in earlier form, but a genuinely different place, capable of making objects that have no modern name. That is humbling. It suggests that the cosmos still has whole categories of things to show us, hidden in the eras we are only now able to see. But whichever suspect you favor, whether dusty starburst or feeding black hole or something new, there is a deeper problem lurking underneath all three. And this is where the mystery darkens into something that genuinely unsettles cosmologists. The problem is one of time. Whatever the dots are, they seem to be too much, too soon. Consider the black hole interpretation, the leading one. If the dots harbor supermassive black holes, and if those black holes are as massive as the broad lines first suggested, then the early universe was full of enormous black holes, millions or even more times the mass of our sun, already grown to that size within the first several 100 million years after the Big Bang. And here is why that is a crisis. Black holes grow by feeding, by pulling in matter, and there is a speed limit on how fast they can feed, set by the physics of radiation pushing back against the infalling gas. There simply may not have been enough time in those first few 100 million years for black holes to grow from ordinary beginnings to such enormous sizes at the allowed rate. It is like meeting a child who is only a few months old and already the size of a grown adult. Either they grew impossibly fast, or they started far larger than a newborn should, or something about our understanding of how they grow is wrong. This is the seed problem, and it is one of the great open questions of cosmology, made sharper and more urgent by the dots. How do you make a supermassive black hole so soon? To have such large black holes so early, you may need them to have started from unusually massive seeds, perhaps from the direct collapse of huge clouds of gas into black holes without ever forming stars first, or from some other exotic early channel. Or you may need them to have fed faster than we thought possible, breaking the usual speed limit through some special early condition. Or, again, you may need a new idea entirely. The dots take this already difficult problem and multiply it, because there are so many of them. It is hard enough to explain a few enormous early black holes. The dots suggest the early universe was full of them, and the same kind of trouble haunts the galaxy interpretation. If the dots are galaxies, they seem to be too massive and too dense for their age, packing more stars into a smaller space earlier than our models of galaxy assembly comfortably predict. Either way, black hole or galaxy, the dots seem to be telling us that the early universe built big, concentrated, massive things, faster than our careful theories of cosmic growth allow. That is why, in the first wave of these discoveries, some astronomers spoke half seriously of objects that might break the models. The dots became emblems of a broader unease, a sense that the cosmic dawn Webb was revealing was richer and more precocious than we had been prepared for. A universe that grew up faster than its own rules seemed to permit. This is the dark heart of the mystery, the place where it stops being a charming puzzle about little red points and becomes a genuine challenge to our understanding of how everything we see was built. If the dots are real, and they are, and if they are as massive and as early as they first appeared, then something is missing from our story of the universe's beginning, and that is the tension that the newest research has been racing to resolve. Because there is, it turns out, a way to read the clues that holds them together, that quiets the contradictions, and that even tames the crisis of too much too soon. It is the idea that has risen over the last couple of years to become the leading explanation. And it begins by taking that strange V-shaped light and those broad lines and that quiet in the X-rays and asking what single peculiar object could produce all of them at once. The answer has a strange and wonderful name. Let us go and meet the black hole star. Before we meet that strange new object, let us stay a little longer in the dark heart of the problem, because the trouble the dots cause runs deeper than a single puzzle, and feeling that depth is what makes the eventual resolution so satisfying. Let me make the black hole growth problem vivid, because it is at the center of everything. Picture a black hole trying to grow by feeding. As gas falls toward it, the gas heats up and shines fiercely. And here is the catch, the beautiful self-limiting catch of nature. That outpouring of light pushes back on the gas that is still trying to fall in. Light exerts a gentle pressure, and when the feeding gets intense enough, the pressure of the escaping light becomes strong enough to hold back the infalling gas, choking off the supply. The black hole, in effect, blows away its own meal when it tries to eat too fast. This sets a natural speed limit on how quickly a black hole can grow, a ceiling that astronomers have a name for. And under that ceiling, growing a black hole from a modest beginning to millions of times the mass of the Sun takes time a great deal of time, more time, by the simplest reckoning, than the few 100 million years available in the era of the dots. So if the dots really do contain black holes that massive, that early, you face a hard choice among uncomfortable options. Perhaps the black holes did not start small. Perhaps, in the special conditions of the very early universe, enormous clouds of gas collapsed directly into large black holes, skipping the star stage entirely, beginning life already heavy, with a running start of tens of thousands of solar masses. This is the direct collapse idea, and it is elegant, but it requires special conditions and is not fully understood. Or perhaps the black holes did start small, from the deaths of the first massive stars, but then fed faster than the usual ceiling allows, in brief, furious episodes that broke the speed limit under early conditions we do not yet grasp. Or perhaps, once again, something is wrong with our assumptions, and the answer is stranger than any of these. The dots force the question and refuse to let it rest because there are so many of them. A handful of overgrown early black holes might be explained away as rare flukes. A whole abundant population cannot. And it is worth placing the dots in their larger context because they did not arrive alone. When Webb first turned its eye on the cosmic dawn, the dots were part of a wider wave of surprises. The telescope kept finding galaxies that seemed too bright, too massive, too well formed for how early they were. Again and again, the early universe Webb revealed looked more mature, more developed, more precociously grown up than our models had led us to expect. The dots were the sharpest and strangest example of this broader pattern, but they were not isolated. They were part of a growing sense that the first chapter of cosmic history was a more vigorous, more productive, faster building time than we had imagined. Some of those other surprises have since been softened by better measurements, as early excitements often are. But the dots have stubbornly remained, holding their mystery, refusing to be explained away. Let yourself feel for a moment what this kind of challenge means for the people whose life work is building these models. For decades, cosmologists have assembled a remarkably successful picture of how the universe grows, how tiny ripples in the early cosmos drew matter together under gravity, how those gathering clumps formed the first stars and then the first galaxies, how structure built up step by patient step into the grand cosmic web we see today. It is one of the great intellectual achievements of our species, and it works astonishingly well across most of cosmic history. And then Webb opens its eye on the dawn, and there are these dots, abundant and contradictory, and seemingly too grown up for their age, and they sit there in the data like a question that will not be dismissed. There is something both humbling and exhilarating in that, to have built so beautiful a theory, and then to be shown by the universe itself a corner of reality the theory did not quite anticipate. That is not failure. That is the universe handing us our next lesson, and the dots are the lesson written small and red across the early sky. I do not want to overstate the crisis, because honesty cuts both ways, and the most recent work has gone a long way toward calming it, as we are about to see. But I also do not want to understate how real the tension was, and in some ways still is. For a stretch of time, the little red dots looked like they might genuinely break our picture of the early universe, like they might be telling us that black holes or galaxies grew in ways our physics could not account for. That is a serious thing to face. It is the kind of anomaly that, in the history of science has sometimes cracked open into revolution and sometimes dissolved into a subtle measurement error once someone found the missing piece. Which of those the dots will be, we are still finding out. But the search for the answer has produced an idea so elegant that even if it turns out not to be the whole story, it deserves to be understood, because it shows how a single clever insight can take a table full of contradictions and quietly make them agree. It is worth pausing to admire the shape of the moment we have reached, because it is the most honest part of any mystery. We have 3 suspects, and each one is partly guilty and partly innocent. We have a deep, underlying problem of too much, too soon, that none of the 3 fully resolves. And we have a table of clues that no familiar object holds together. This is the point in a real investigation, where progress comes not from forcing an old answer to fit, but from imagining a new arrangement of the same pieces, one nobody had quite pictured before. That is exactly what happened. The breakthrough did not come from finding new evidence. It came from looking at the evidence we already had, the V-shaped light most of all, and asking what one strange object could make all of it at once. The key to that idea is the strangest clue of all, the one we have been carrying since the start of our forensic work, the V-shaped light. The fact that each dot is somehow both red and blue, with a dip between, as though 2 different sources of light were shining from the same tiny point. And the second key is to take seriously, rather than explain away, the broad lines and the missing X-rays together, to ask not how to dismiss one of them, but what single object would produce broad lines and yet stay quiet in X-rays at the same time. When astronomers stopped trying to force the dots into an existing category and instead asked what new configuration could produce the whole strange combination at once, they arrived at a picture that is genuinely new and genuinely beautiful, and that even reaches back to tame the crisis of too much too soon. A black hole, yes, but not a naked feeding black hole blazing in the open. A black hole wrapped, swaddled, buried inside an enormous dense cocoon of gas, so thick that it glows like the surface of a vast star. A black hole hidden inside a star-sized atmosphere of its own making. They call it a black hole star, and it may be the answer. Let us go and see how it holds the whole riddle together. Imagine a supermassive black hole in the young universe, feeding hungrily, but instead of sitting in the open, blazing nakedly for all to see, imagine it buried inside an enormous, dense, swirling cocoon of gas. So much gas, so thick and so close, that the black hole is wrapped in it the way a seed is wrapped in fruit. The fierce light from the feeding does not escape directly. It pours outward into the surrounding gas, and the gas absorbs it and reprocesses it and re-emits it, so that what finally leaks out to us is not the raw glare of the black hole, but the glow of the whole vast gas envelope, lit from within. And that envelope, heated by the buried engine, glows across its enormous surface, almost the way the surface of a star glows, a black hole wearing a star-sized atmosphere. This is the black hole star, and it may be what a little red dot truly is. Let us see how this one strange picture reaches out and touches every clue on our table, because the elegance is in how much it explains at once. Start with the V-shaped light, the deepest puzzle, the redness and blueness together. In the black hole star picture, the thick gas envelope has structure. Its outer layers, cooler and dense, glow red, producing the strong red light that gives the dots their name. But not all the light is reprocessed by the cool outer envelope. Some light escapes through gaps, or scatters off the outer edges, or comes from cooler stars in the surrounding host, and this contributes the blue component. The result is light with two characters, a red glow from the dense reprocessing envelope and a bluer component from the light that escapes more directly, blended in the same tiny source. The V shape, blue and red with a valley between, falls out naturally from a buried engine inside a thick glowing shroud. The clue that fit no simple object fits this one. Now take the broad hydrogen lines, and here is the most beautiful and subtle part of the whole idea, the insight that quietly dissolves the crisis. We assumed, reasonably, that the broad lines meant gas whirling at thousands of kilometers per second, dragged around by a tremendously massive black hole. The width of the lines told us the speed, and the speed told us the mass, and the mass was alarmingly large. But there is another way to broaden a spectral line, and it has nothing to do with the gas moving fast as a whole. It is called electron scattering. In a dense cocoon of hot ionized gas, gas so hot its atoms have been stripped of their electrons, light does not travel straight out. It ricochets, bouncing off free electron after free electron, like a ball pinging through a dense crowd, each tiny collision nudging its wavelength slightly. By the time the light finally escapes the cocoon, those countless small nudges have smeared its sharp lines out into broad ones. The line is broadened not because the gas is whirling at enormous speed, but because the light has been scattered 1,000,000 times on its way out through a thick envelope of electrons. Feel what this does to the whole problem. If the broad lines come partly from electron scattering rather than purely from fast whirling gas, then we have been overestimating how fast the gas moves, which means we have been overestimating the mass of the black hole needed to whirl it. The broad lines are real, but they do not require the monstrous masses we feared. A more modest black hole, wrapped in a dense scattering cocoon, can produce lines just as broad as a giant one in the open. The terror of too massive too soon was, at least in part, a mirage created by the cocoon itself, the very gas envelope that defines these objects, fooling us into thinking the black hole inside was larger than it is. And this is exactly what the most recent work has found. And it is worth stating plainly because it is the heart of the resolution. When astronomers carefully accounted for electron scattering in the cocoon, the implied masses of the black holes dropped, and dropped sharply, by something like a factor of 100, a 100-fold reduction. Black holes that had seemed to be hundreds of millions of times the mass of the Sun, impossibly large for their age, were recalculated to be far smaller, in a range of perhaps 100,000 to a few million solar masses. And here is the relief, the quiet click of a lock opening. Black holes in that corrected, smaller range are no longer impossible. They fit comfortably within what our standard models of early cosmic growth can produce in the available time. The crisis of too much, too soon eases. The dots stop breaking the universe. The same cocoon that hid the black hole and reddened its light and broadened its lines had also inflated our estimate of its mass, and once we corrected for it, the monster shrank to something the early universe could plausibly have made. Now take the two great absences, the missing X-rays and the missing hot dust, and watch them resolve too. The X-rays, A naked feeding black hole blazes in X-rays, but a black hole buried in an immensely thick cocoon of gas is different. That dense envelope can absorb and smother the X-rays, soaking them up before they ever escape, so that from outside the object looks quiet in X-rays, even though a real feeding black hole roars within. The cocoon muffles the high-energy light. The silence in the X-rays, which seem to argue against a black hole, is exactly what you would expect if the black hole is wrapped thickly enough. And the missing hot dust. Recall that we worried the reddening could not be explained by a dust shroud, because such a shroud should glow hot, and it did not. But in the black hole star picture, the reddening is not done by dust at all. It is done by the gas, the dense glowing envelope itself. There is no need for a thick dust shroud, so there is no missing hot dust glow to explain. The reddening comes from gas, not dust, and the absence that puzzled us simply dissolves. Do you see what has happened? One picture, a black hole swaddled in a dense glowing cocoon of gas, reaches out and accounts for the whole contradictory table at once. The V-shaped light, the compactness, since the whole glowing envelope is still small, the broad lines through scattering, the quiet X-rays through absorption, the missing hot dust, because gas not dust does the reddening, and the crisis of mass eased by the very scattering that broadened the lines. Clue after clue, the contradictions fall into agreement under this single strange idea. That is what a good explanation feels like. Not a patch over one problem, but a key that turns every lock at once. And the evidence for it has been mounting. The highest quality spectra, taken of the brightest and best placed dots, including cases where a foreground galaxy acts as a natural lens, bending and magnifying the dot's light so we can study it in unprecedented detail, have shown the particular signatures that the black hole star picture predicts, the fingerprints of light that has been reprocessed and scattered in a dense ionized envelope rather than emitted by fast whirling gas in the open. Each such observation has strengthened the case. By the most recent work, the black hole star has moved from a clever proposal to the leading explanation, the frontrunner that holds the most clues together with the fewest contradictions. But I promised you honesty, and honesty requires me to say clearly that this is not a closed case. The black hole star is the leading idea, not the final verdict. Science does not work by sudden certainty, and the dots are still being studied intensely. There are real and serious alternative ideas still in play. Some researchers argue that at least a portion of the dots may be better explained as extremely dense young star clusters in the act of forming, immense globular clusters being born, which could mimic some of the same features. Some argue that the population is mixed, that there is no single answer, that some dots are buried black holes and others are something else, and that we have been treating as one phenomenon what may be several. And even within the black hole star idea, many details remain to be worked out. The exact structure of the cocoon, how it forms, how long it lasts, why it appears so abundantly in the cosmic dawn and then fades. The picture is coming into focus, but the image is not yet sharp. Still, sit with the satisfaction of how far we have come, because it is real. We began with a contradiction that seemed to threaten our understanding of the early universe. Objects that looked impossible, too massive and too early and too strange. And through careful work, through taking the weirdest clue seriously and asking what single object could produce the whole pattern, we have arrived at a picture that not only holds the contradictions together, but tames the crisis that made the dots so alarming in the first place. The monsters that threatened to break the models turned out, very possibly, to be more modest black holes wearing disguises of glowing gas, disguises that fooled our instruments into seeing giants. That is how science often heals its own crises. Not by overthrowing everything, but by finding the subtle effect that was fooling us and correcting for it until the impossible becomes merely difficult and the difficult becomes understood. But the black hole star, even as it answers what the dots are, opens onto a larger and gentler question, the question of what they mean. Because if these are indeed young black holes in glowing cocoons, scattered in their thousands across the cosmic dawn, then they are telling us something profound about the universe's first chapter, about how the first great engines of light and gravity switched on, and about the deep origins of everything that came after, including the galaxy we live in and the star we orbit. Let us follow that thread in our final stretch, out from the mystery itself toward the meaning hidden inside it. Let us linger on the black hole star itself a little longer, because it is one of the more wonderful objects ever proposed, and it deserves to be pictured properly. Try to see it in your mind. At the center, a black hole, a region where gravity is folded so deeply that not even light escapes. Perhaps 100,000 or a few million times the mass of the Sunday. Around it, not empty space, not a thin disk, but an immense, dense shroud of gas, hot and ionized, glowing from the energy of the feeding within. The whole thing is enormous, and yet, by cosmic standards, compact, a single concentrated source. From far away, across 13 billion years, it would look like nothing but a tiny red point. But up close, it would be a strange and awesome sight. A glowing sphere of gas the size of a small galaxy's heart, lit from within by an engine you could never see directly, the black hole forever hidden inside the light it powers. It is almost a paradox made real, the darkest object in nature wrapped in one of the brightest, the void clothed in fire, shining precisely because of what it is devouring. There is a lovely historical echo here too, the kind that makes you feel the long memory of science. Decades ago, long before Webb, before anyone had seen a little red dot, some theorists played with the idea of objects very much like this, hypothetical configurations sometimes called quasi-stars, in which a young black hole sat buried inside a vast envelope of gas that glowed like an enormous star. It was a theoretical curiosity then, an idea on paper, a thing the early universe might in principle have made. And now, generations later, Webb may have actually found them in abundance, scattered across the cosmic dawn. There is something deeply satisfying in that, an idea imagined in the quiet of theory, set aside, and then met face to face in the data many years later. The universe, it seems, had been making these things all along, and we simply could not see them until we built an eye that could catch their ancient reddened light. And the black hole star may do more than explain the dots. It may help solve the very seed problem that made them so alarming. Remember the puzzle of how black holes grew so big so fast. One proposed answer was direct collapse, the idea that huge clouds of gas in the early universe collapsed straight into massive black holes, without first forming stars, giving the black holes a heavy head start. The black hole star picture fits naturally with that story. A black hole born heavy by direct collapse, still embedded in the enormous cloud of gas it formed from, feeding on that gas while wrapped inside it, would look exactly like a black hole star. So the dots may be showing us the early, embedded, gas-swaddled phase of black hole growth, the stage when a young black hole is still buried in its birth cloud, feeding and glowing, before it later blows away its envelope and emerges as the kind of naked, X-ray bright feeding black hole we are familiar with from the later universe. In this view, the dots are not a separate species at all. They are a life stage, the infancy of supermassive black holes, caught in the act. A phase every great black hole may have passed through and then left behind. That would explain why they are so common in the cosmic dawn and then fade. They do not vanish, they grow up. They shed their cocoons and become the ordinary black holes and galactic centers of the mature universe, including, perhaps, the giant black hole that sits quietly at the heart of our own galaxy today. Let that thought settle, because it is a beautiful one. The strange red dots at the edge of the universe may be baby pictures, not just of the cosmos in general, but of black holes specifically, the swaddled infancy of the very engines that anchor galaxies like ours. The monster at the center of the Milky Way may once have been a little red dot, glowing in its cocoon in the cosmic dawn, before it grew and settled and the gas cleared. We may be looking at our own galaxy's deep ancestry, at the kind of object from which our cosmic home was, in part, assembled. And the research is still moving week by week, which is part of what makes this such a thrilling time to pay attention. Even very recently, new analyses have refined the picture, some suggesting that the feeding of these buried black holes may come in bursts rather than a steady flow, brief, intense episodes of accretion that could explain certain variations in the dot's light. Others continue to test the black hole star idea against the sharpest available spectra, including those rare cases magnified by gravitational lensing, where a foreground mass bends and brightens the dot's light and lets us see it in extraordinary detail. Each new observation either tightens the case or reveals a new wrinkle to be understood. This is not settled history. This is live science, unfolding now, and the picture we have tonight is the best current reading of a story still being written. A year from now, it may be sharper. It may even have turned. That is not a weakness of the science. It is the very pulse of it. There is a humility worth holding on to in all of this, even amid the excitement. The dots have already humbled us once by appearing where no theory expected them, and they have been tamed once by the discovery that the cocoon was inflating our estimates. A good scientist keeps both of those lessons in mind at the same time, the readiness to be surprised and the patience to be corrected. The black hole star may be the answer. It may be most of the answer. It may, in some final accounting years from now, be only part of it. Holding that openness is not a failure of nerve. It is the discipline that let us get this far. So where does that leave us, honestly? It leaves us with a leading explanation that is elegant and powerful and growing stronger. The black hole star, a young supermassive black hole wrapped in a dense, glowing cocoon of gas, an object that holds nearly all the contradictory clues together and tames the crisis of early growth by revealing that the masses were overestimated all along. It leaves us with real alternatives still in play: dense forming star clusters, mixed populations, details unresolved. And it leaves us, most importantly, with a sense that the dots are no longer quite the impossible, model-breaking monsters they first appeared to be, but something more wonderful, a glimpse of the embedded infancy of the universe's first great black holes, caught in the brief glowing phase before they grew into the anchors of galaxies. That is an extraordinary place to have arrived, from a handful of tiny red points that you would have scrolled right past. But there is one more move to make, the move from what and how to why it matters, from the mechanism to the meaning. Because these dots, whatever their final explanation, are letting us watch the universe build its first great structures, and that is a story that includes us. Let us close by following it home. So what does it all mean? We have chased the little red dots from a single point in an image to the edge of the observable universe, through a table of contradictory clues, past three imperfect suspects, into the elegant strangeness of the black hole star. But underneath the question of what they are lies a larger and quieter question, the one that makes this whole story matter beyond the technical thrill of solving it. What are the dots telling us about the universe we live in, and about how everything we know came to be? Begin with the first billion years, the era the dots inhabit, because that era is the foundation of everything. We sometimes think of the early universe as a kind of dim prologue, a vague and formless time before the real story of stars and galaxies began. But it is the opposite. The first billion years were the most consequential stretch in all of cosmic history, the time when the universe laid down its foundations, when the first stars ignited, when the first galaxies assembled, when the first black holes formed and began to grow. Everything that came afterward, all the long ages of cosmic evolution, every galaxy and star and planet that would ever exist, was built on what happened in that early chapter. It is the bedrock, and it has been, until very recently, almost entirely hidden from us, too distant and too faint to study in detail. The dots are one of our first clear views of it, and what they show us is that the early universe was busier, faster, and more creative than we had assumed. If the dots are the embedded infancy of supermassive black holes, then they are telling us that the universe began building these great gravitational engines almost immediately in its first few 100 million years, far earlier and far more abundantly than the older picture suggested. The first black holes did not wait politely for galaxies to mature around them. They formed early, fed furiously inside their cocoons of gas, and grew. And in growing, they shaped the galaxies forming around them. This matters enormously, because in the universe we see today, the giant black holes at the centers of galaxies are intimately connected to the galaxies themselves. Their growth and the galaxy's growth are linked, woven together, each influencing the other. The dots may be showing us the very beginning of that relationship, the first moments of the long partnership between black holes and galaxies that has shaped cosmic structure ever since. Let me make that personal, because it is. Our own galaxy, the Milky Way, has a supermassive black hole at its center, a giant several million times the mass of the Sun, sitting quietly now, mostly dormant, in the heart of our spiral. That black hole was not always quiet, and it was not always there at full size. It grew over billions of years, from some early seed, through epochs of feeding and growth. And if the black hole star picture is right, then there may have been a time in the cosmic dawn when the ancestor of our galaxy's central black hole was itself a little red dot, a young black hole glowing inside a dense cocoon of gas, one of those crimson points that a future astronomer in some distant galaxy might have seen in their own deep images and wondered about. The dots are not alien to us. They may be our own deep origins, the infancy of the kind of object that anchors our cosmic home. When we study them, we are studying the childhood of galaxies like ours, and in a real sense, the childhood of the structures that made us possible. Now widen the lens all the way to the largest view, because this is where the dots stop being an astronomy puzzle and become something closer to philosophy. Consider again what we are actually doing when we look at one of these objects. We are catching light that left its source more than 13 billion years ago. Light that has been traveling across expanding space for almost the entire age of the universe. Light that set out when there was no Earth, no sun, no solar system, when the matter that would become us was not yet gathered into anything. That light has crossed an almost incomprehensible gulf of time and space, and ended its journey on a mirror of gold that a curious species built and flung into the cold dark beyond the moon. And in that ancient light, we are reading the story of the universe's infancy. Let that sit fully, because it is one of the most extraordinary things our species does. We are made of atoms forged inside stars that lived and died long before the sun existed. We sit on a small wet world in the last sliver of the cosmic year. And from here, with patience and ingenuity and a great golden eye, we reach back across the entire history of the universe and look upon its first chapter, upon the very era when the structures that would eventually give rise to us were first taking shape. The little red dots are a message from that era. They are light from the dawn, and we have learned to read it. There is a kind of reverence appropriate to that, a quiet astonishment that the cosmos should be knowable at all, that its infant light should still be arriving, and that beings made of its old star stuff should be here to catch it and wonder. And there is something consoling too in the particular shape of this mystery, something gentle hidden inside the vastness. The dots began as a crisis, as objects that seemed impossible, that threatened to break our understanding, that whispered that the universe did not work the way we thought. And the response was not panic, and not the collapse of our knowledge, but patient, careful, collaborative work, the slow turning of the evidence until a new and more beautiful understanding emerged. The impossible monsters became, very likely, the glowing infancy of ordinary black holes, disguised by a trick of scattered light. The crisis became a deeper understanding. That is a hopeful pattern, and it is the pattern of science at its best. The universe hands us something that does not fit, and instead of breaking us, it teaches us, and we come out the other side knowing more and seeing further and feeling smaller in the best possible way. There is another thread worth following before we close the loop, because it deepens the meaning of these objects still further. The era of the dots, the cosmic dawn, was not only the time when the first stars and black holes formed, it was also the time when the universe changed its fundamental character, when it went from dark to clear. In the early ages, the gas filling the cosmos was a thick neutral fog, opaque, the way mist is opaque, and that fog had to be burned away before light could travel freely across space. The first sources of intense radiation, the first stars, and the first feeding black holes poured out energetic light that gradually stripped the electrons from that fog, clearing it, making the universe transparent for the first time. Astronomers call this great clearing the epoch of reionization, the dawn when the cosmic fog lifted. And the little red dots, if they are early feeding black holes glowing in their cocoons, may have played a part in that clearing, contributing to the radiation that swept the fog away and opened the universe to light. They may be not just witnesses to the cosmic dawn, but participants in it, among the very sources that turned the lights on. To study them is to study how the universe became the transparent, star-filled, observable place we now inhabit. Hold the scale of that for a moment, because it is worth feeling fully. We are talking about the transition from a dark, formless, foggy cosmos to the structured, luminous universe of galaxies. That transition happened once in the deep past, and it set the stage for everything, and we are now, for the first time, able to look directly at the objects that lived through it and perhaps helped drive it. For almost all of human history, the cosmic dawn was utterly beyond reach, a thing we could only theorize about, a darkness we could not pierce. Now there are crimson points in our images that come from precisely that era, and we are reading their light and arguing about their nature, and slowly piecing together the story of how the lights came on. That is a threshold our species has only just crossed. We are the first generation of humans able to see this far back with this much clarity. The little red dots are among the first detailed messages we have ever received from the universe's first chapter, and the story is only beginning. The telescope that found the dots will keep staring, gathering deeper images, taking sharper spectra, finding fainter and stranger examples. New instruments and new surveys are being planned to study these objects in still greater detail, to measure their light across more wavelengths, to catch the ones magnified by gravitational lensing, to test the black hole star idea against ever finer data. In the coming years, we will almost certainly learn whether the leading explanation holds, whether the dots are uniformly young black holes in cocoons or a mixed population of several kinds of object, whether some are forming star clusters, whether the masses settle where the recent corrections place them. The mystery is not closing so much as deepening into a rich field of active study, the kind of subject that will fill papers and conferences and careers for years to come. We happen to be alive at the moment it opened. That is a piece of luck, a small gift of timing, to be paying attention to the sky during the very years when one of its old secrets is beginning to give way. And let me say one more quiet thing about time, because it underlies everything we have explored. The dots force us to hold two time scales at once, and the holding is part of the wonder. On one hand, there is the unimaginable span of cosmic time, the more than 13 billion years the light has traveled, a duration so vast that the entire history of life on Earth is a thin sliver near its end, and a human life is less than a flicker. On the other hand, there is the swiftness of our own understanding, the fact that this entire story, the discovery of the dots, the naming, the debate, the crisis, the black hole star, the mass correction, has unfolded in just the last few years, a span you could measure against the age of a child. The oldest light in the universe, decoded, in the blink of a few seasons. The deepest past, read in the immediate present. There is a strange beauty in that meeting of the slowest and the fastest of timescales, the ancient light and the rapid understanding, converging on a golden mirror and in a handful of human minds. We live at the hinge where the two meet. It is worth saying too that this whole story is a human achievement as much as a cosmic one, and that is part of what makes it consoling rather than merely vast. No single person solved the mystery of the little red dots. It was found by teams sifting through enormous surveys, named by researchers comparing notes, debated in papers written by people in many countries, challenged and defended and refined by a global community of scientists who mostly will never meet. The electron scattering insight, the mass correction, the lens spectra, each piece was contributed by different minds, building on one another, arguing in good faith, correcting one another with care. When you look at a little red dot and understand even a little of what it might be, you are holding the collective work of a great many patient people, the slow accumulated effort of a species trying, together, to understand where it came from. There is something deeply moving in that. The idea that the reading of the universe's first light is a shared labor, handed from one mind to the next, no one owning it, everyone adding to it. And it is worth holding the simple strangeness of our situation in the cosmos, because the dots bring it into focus. We are latecomers. We arrived in the final sliver of the cosmic year, on a small planet around an ordinary star, in a galaxy that is one among uncountable billions. By every measure of size and time, we are almost nothing, a brief flicker of awareness on a speck of rock. And yet this brief flicker has built an instrument that can catch light from the universe's infancy, and a mind that can wonder what that light means, and a community that can slowly decode it. The dots remind us of our smallness and our reach at the same time, in the same breath. We are tiny, and we are the part of the cosmos that has learned to look back at its own beginning. Both things are true, and holding them together is, I think, the truest feeling that astronomy can give. Not pride and not despair, but a kind of quiet, humble astonishment at being here at all, awake, able to ask. So let us return, at the end, to where we began, to a single, deep image from the James Webb Telescope, a black field strewn with galaxies, thousands of them, spirals and smudges and golden ovals, and somewhere in that field, easy to overlook, a tiny red dot. When we started, it was just that, a small red point you would scroll right past, a curiosity. But look at it now, with everything we have learned. That little red dot may be a supermassive black hole in its glowing infancy, wrapped in a dense cocoon of hot gas, feeding in the first hundreds of millions of years of cosmic time. Its light has traveled more than 13 billion years to reach the screen you are looking at. It is a glimpse of the universe building its first great engines, perhaps a glimpse of the kind of object from which galaxies like our own were grown. It is a message from the dawn, still being decoded by people working carefully and arguing kindly and slowly turning a mystery into knowledge. It is not just a dot anymore. It never was. It only looked like one, the way the most extraordinary things sometimes wear the plainest faces, waiting for someone patient enough to look closely. That is the gift the little red dots have given us, beyond any particular answer. They have reminded us that the universe still holds surprises in plain sight, that even the most powerful telescope ever built can look at the sky and find something it cannot immediately explain, that the cosmic dawn is not a closed book, but a chapter we are only beginning to read. They have reminded us that wonder and rigor belong together, that a mystery is not a thing to fear, but a thing to follow, patiently, clue by clue, toward understanding. And they have reminded us that we, small and brief as we are the part of the universe that has learned to look back at its own beginning and ask what it sees. And perhaps that is the deepest thing the dots offer, more lasting than whatever the final answer turns out to be. They are proof that the universe is still willing to surprise us, that even now, with our great telescopes and our careful theories, we can look at the sky and find something we do not understand, something that sends a generation of brilliant people back to their equations and their spectra to think again. A universe that can still do that to us is a universe worth living in, a universe that has not run out of secrets, a universe that keeps the door of wonder open. The little red dots are a knock on that door from 13 billion years away. We are only beginning to answer it. So the next time you come across one of those deep images, the kind strewn with distant galaxies, let your eye wander until it finds one of the small red points among them. Rest there for a moment. Remember that you are looking across almost the entire age of the universe, at light that began its journey before the Earth was born, at an object that may be the glowing infancy of a black hole, at a piece of the puzzle of how everything we know came to be. And then let yourself feel, quietly, the strange and lovely fact that you live in a universe that can be looked at this way, by minds that can hold its dawn in their attention, and that you are one of those minds, here, now, awake, watching the first light still arriving. Let that be enough for tonight. The dots are out there, glowing across the dawn of time, patient as they have always been, and we are here, finally, learning to read them.